Okay, so for the next point problem, it says to find all of the critical points of f. So if I want to find the critical points of this, I need to take their derivative and set it equal to 0. So I'll say 0 equals, and then the derivative of that is going to be 12x cubed minus 72x squared plus 108x. So to solve this, I'm just going to go ahead and factor out some things. So I think I can factor out a 12x, and I'm left with x squared minus 6x plus 9. And so then I can factor that further. X squared minus 6x plus 9 factors to x minus 3 times x minus 3. So it's x minus 3 squared. And so our solutions are x equals 0 from this one, and x minus 3 equals 0, which is just x equals 3. And that's because of the zero product property. Since I have these things multiplied together equal to 0, if I have two things multiplied together equal to 0, it means that one of those two things must equal 0. So either x equals 0 or x equals 3. And then it says determine the absolute minimum of f of x on that interval. So what I need to do for this is I need to check the value at the endpoints and the critical points. So I can say f of minus 1. I can find f of 0. I can find f of 3. And I can find f of 4. And one thing to note is that the two critical points that I found happen to lie within this interval. If they did not lie within that interval, then I wouldn't consider them as relevant for that interval. So I would just throw them out. But in this case, my two critical points actually do lie in the interval, so I can consider them. So when you plug -1 into the function, you get 81. When you plug 0 in, you get 0. When you plug 3, I'm plugging them into the function f again. When I plug in 3 into that function, I also get 81. When I plug in 4, I get 96. So we can say that f of x has a global max of 96 at the point x equal 4. And I can say f of x has a global min, and again, it's on the interval -1, 4, of the minimum value is 0. So this is the smallest, and this is the biggest at x equals 0. So at x equals 0, it achieves its minimum value of 0. At x equal 4, it achieves its maximum value of 96. So this one says, evaluate the following limits or state whether they do not exist. So, so if I notice on this one, it's theta is going to pi. So the first thing we want to do is, if this happens to be a continuous function, I should just be able to plug in the value of pi. Well, what happens if I just plug in the value of pi? Well, if I plug in pi in the numerator, I get sine of pi, which I know is 0. In the denominator, I'm going to get what? Okay, tangent of pi is 0. So e to the 0 will be 1. Cosine of pi is -1. So I'll get 1 plus -1, so I'll get 0 in the denominator. So I'm noticing that at pi, I'm getting this indeterminate form of 0 over 0. So because of that, I'm allowed to apply L'Hopital's rule. So let's just note that this is an indeterminate form of 0 over 0. So that gives me the justification to be able to use L'Hopital's rule. So I'm going to say that that equals, and the way I tell my students to indicate this is just writing an L apostrophe H over the equal sign. So this is equal to, by L'Hopital's rule, limit as theta goes to pi of, and I can take the derivative of the numerator, which will give me cosine theta, and then the derivative of the denominator, which will give me, so it will give me e to the tangent theta times the derivative of tangent theta, which is secant squared theta. That's by the chain rule, plus the derivative of cosine theta is negative sine theta. Okay, so does that fix my problem? Now what happens if I just plug in pi in the numerator? Cosine of pi is -1, so okay, that's problem is fixed in the numerator. What about in the denominator? Tangent of pi is still 0, so I'll get e to the 0, which is 1, and then secant squared, let's see, secant is the reciprocal of cosine, so it should be 1 over -1, but when I square it, I just get a 1. So I'll just have a 1 down there, plus, and then negative, and then at theta, when theta equals pi, sine theta again is 0. So if I can go ahead and compute this at this point. So I'll have -1 over, I'll just write it out, e to the 0 times -1 squared minus 0, which is just going to give us -1 over 1, which is -1. So that's that's what our limit is. Okay, in the top here, or in the next one, let's see what's going to happen. As x goes to 5, so natural log of x over 5, okay, if I just plug in a 5 there, that would be natural log of 1, which I know to be 0, and pi to the x minus 5, so that would be pi to the 5 minus 5, which would be pi to the 0, and any number to the 0 power is 1. So this actually ends up giving me 0 over 1, which is just 0. So this function is actually continuous at 5, so I can go ahead and plug it in. Okay, compute the following derivatives. I want to find f prime. Okay, so it looks like I have I have a quotient here, so I'm going to need to apply the quotient rule. So my f prime is going to be, it's going to be the bottom function times the derivative of the top minus the top function times the derivative of the bottom. I like to write out the parentheses ahead of time and then fill them in. So the bottom will be easy, the x to the 7th squared. Okay, and on the top, it's going to be x to the 7th times the derivative of 7 to the x. So that's going to be 7 to the x times the natural log of 7. Minus 7 to the x, and then the derivative of x to the 7 will be 7x to the 6th over 7x squared. So that is our derivative, and I would just leave it just like that. It'll be nice and easy for your instructor to grade if you don't simplify, and if you simplify, you're at the risk of making an error, so I would just leave it just like that. Okay, for the next one, I have y equals natural log of secant x, and I need to find the second derivative. Okay, so y prime is going to be, well, I'm going to use chain rule here, so I'll have 1 over secant x times the derivative of secant is secant x tangent x. And this actually will simplify to just tangent x. And then the second derivative, y double prime, is going to be the derivative of the derivative. So the derivative of tangent x is secant squared x. And that's all for this video.